let's look at this one. So another natural log one. We have the limit as x goes to infinity of natural log x over the cube root of x. So very first step, as usual, we need to check the form. See what's going on with our limit. Now x here is approaching infinity, so we can't really just plug in infinity. Infinity is not a number that we can just plug into functions. So we need to investigate, well, what is the term in the top doing? And what is the term in the bottom here doing when x gets really large? So we're going to investigate here. And so by itself, natural log, if the input here of our function is getting really big, well then the natural log function also gets really big. So the top here is going to infinity. Now what about the term in the denominator? If x gets really big, well then the root function here also gets really big. So we have infinity over infinity form. And that's the correct format for L'Hopital's rule. And by itself, though, this is not our answer. Infinity over infinity, it's indeterminate. So this is not the answer. We have to stop here. Stop. Don't go any further with this line of reasoning here. This is not our answer. But we can use L'Hopital's rule now. All right, so we apply the rule. All right, so let's write down our limit now. As x goes to infinity, natural log x over the cube root of x. And applying the rule, that means we're gonna differentiate the term in the top here, differentiate the term in the bottom. So let's actually apply the derivatives. And while we're going along here, we know we're going to differentiate. We know we normally clean up these root signs. So let's write that as x raised to the 1/3 power. And we're going to apply the derivative there, and we apply the derivative to the bottom. So again, it's not quotient rule. We're not differentiating this entire function. All we're doing is we're differentiating the top, differentiating the bottom, and we're looking at the limit of that fraction. All right, so now we actually differentiate. Derivative of natural log, what was that? That's 1 over x. And then when you get these fractions and you get other fractions on top of fractions, I like to make one of the fractions like my main fraction. So, put a nice big division sign here. Derivative of natural log is 1 over x. And then what's the derivative of this power function? Well, bring the 1/3 down, keep what you have, keep x the same, and then you subtract 1 from the exponent, so you go down to negative 2/3. All right, so there is our brand new limit here. It's a brand new limit. And before we go any further, you can see here we have fractions, we have negative exponents, we have multiple fractions. You want to try to simplify this if you can. So far in the previous examples, there was really nothing to do in terms of simplifying. So here, like in this e to the x one, we went from e to the x over x squared down to e to the x over 2x. Really nothing to simplify. Same thing going back here. We went, using L'Hopital's rule, we went from natural log x over x minus 1 to just 1 over x. Maybe there was a little simplifying we did there, but not too much. So when you get this brand new limit, like what we're seeing in this example, before you start trying L'Hopital's rule again, or before you try to identify what the form is, see if there's anything you can do to simplify. And there's a little bit we can do here. So we can try to get rid of some of these fractions. So there's various ways to think of this. What jumps out at me, I want to get rid of that 1 over x. So what could I do? Well, if I multiplied the numerator here, this 1 over x, by x, that would cancel it out for me. And I can't just do that to just the top. If I'm going to do that, I have to do it to both the top and the bottom of my big fraction here. So I have to also multiply the denominator by x. So we're trying to simplify this. So what do we get? So x times 1 over x is going to be just a 1. Then we have 1/3. We're doing the limit as x goes to infinity. And then x times this x raised to the negative 2/3. What do? We just add the exponents. So there's like a hidden exponent of a 1 here. And when we multiply powers of x, we just add the exponents. So we go from negative 2/3 and we add 1, bumps us up to positive 1/3 down there. All right, so now we have this brand new limit. This is pretty good. I don't think we can simplify this any further. Maybe we could. We have this 1/3. Maybe if we did a times 3 over 3, maybe that would be helpful. But if we're looking at this, what's going on? X is approaching infinity, and now our fraction here, the top is 1, so the top here is just staying a constant 1. And the bottom here is getting really big. So this is a c over infinity form. And so the limit is just 0. So the top is just approaching a constant. Actually, it is constant, but it's approaching some constant. And the denominator here, if x is getting really large positive, the cube root is getting really large positive. So this entire denominator is just getting really big. And so we end up, as x gets larger and larger positive, we end up with this c over infinity form, which we know goes to 0. So there's our answer. And if you were to kind of go back to this step, if we hadn't simplified, 1 over x would go to 0. And then this negative exponent here, we could write that as a fraction. So if we didn't simplify, we would end up with a 0 over 0 form. And then we would just kind of apply L'Hopital's rule. We would end up with kind of larger negative exponents. And so we'd kind of go down the rabbit hole of keep applying L'Hopital's rule, and our function just becomes more and more complicated. So if you get to a point, try to simplify the result before you try using L'Hopital's rule again. And that's what we did here. Brand new limit, try simplifying it first. And simplifying it in this case, we were able to see that now we no longer have an indeterminate form. We can do a little algebra there to write it in a form we recognize. So c over infinity, we know what that's doing. That's going to 0.